Well, hello, welcome back. Glad you guys are here. Today we're going to be looking at simplifying radicals for a review. Before we get involved too far with that, this would be the review notes that we're looking at, 1 through 10. If you don't already have that, you can hit pause here and copy those down. I'm going to be looking at the odd problems here, and then I'll let you work on the even and I'll show you the answers. But before you get too far into that, we need to be very familiar with our perfect squares and our perfect cubes. So I went over to Desmos. Notice I'm using the North Carolina version, so that's what you're used to. And I just typed in y equals x squared and y equals x a third. Now I don't really care about the graphs right now. I'm really more interested in the table. So I'm going to convert that to a table, and I'm going to grab a couple extra values here. All right. These are our perfect squares, and of course there's an infinite amount, there's more than this, but you need to be very familiar with these numbers here. 1, 4, 9, 16, 25, etc. Also, the same thing for our perfect cubes. Now, perfect squares you're probably a little bit more accustomed to. Perfect cubes, maybe not as much. So let's go ahead and review a couple of those real quick. Again, I just changed that to a table, and now I'm going to add a couple more in. Oops. And you can see how easy it is to create that table on your own. So if you're not familiar with that, then please, kind of take a moment here to make a list of those that you are familiar. Back to what we're looking at. I'm going to try to leave those up for you, and at the same time, try to leave that up for you over here. And at the same time, kind of go through some of these. So we're going to start with number 1. Again, I'm going to work on the odd problems. So, number 1. What I want to do is I want to break these up into whichever perfect square over here is on that list. And I recognize that 9 goes into 27. So 9 is a perfect square. So I'm going to rewrite this as the square root of 9 times the square root of 3. 9 times 3 is 27. I'm also going to do the same thing with my with my variables. I'm going to break those up. Since this is a square root, I'm going to do all the perfect squares. So I'm going to do the square root of k squared. Now I have these all broken up into perfects, so at this point I'll simplify. What is the square root of 9? Well, that's a 3. The square root of 3 is not perfect, so I'm going to leave it alone. And the square root of k squared, well, a square root and a square shows that that's perfect, so that's a k. When I put all this together, my perfect numbers out here become my coefficient, and the non-perfect numbers go on the inside. And there's my simplified version. The process works the same with cubed roots. So you can see on number 3, I've got cubed roots. So I'm going to come over here to my Desmos. I'm going to come down to my perfect cubes. So here's my cubes, and here's a list of those. And I'm wondering which one of these numbers will go into 128. Well, I'm going to have to take a calculator and play around for a few minutes. But it turns out that 64 times 2, 64 goes into 128. And you can see that 64 is definitely a perfect cube. So I'm going to rewrite this one as the third root of 64 times the third root of 2. Now, with my variable, when we did number 1, we wanted perfect squares. So on number 3, since this is a third root, I want perfect thirds, so perfect cubes. So I'm going to rewrite this as the cube root of v to the third. And there's more of those, so I still have some more. I'm not up to 7 yet. So here's another v to the third. And then there's one v left over. If you put all that together, there's 3, 6, and then one more here is 7. So that's that v to the 7th. This is perfect. The cube root of 64. As you can see over here, the cube root of 64 is 4. So that's a 4. This one is not perfect. This one is perfect. The cube root of v cubed is a v. And this one is also perfect. So these are my perfect numbers. And I'll put those together for the coefficient. So that's going to equal 4. And since I have 2 v's, that's going to be v squared. The non-perfect ones here go on the inside. So I've got the third root of 2v. The cubed ones tend to be a little bit harder, so we'll stick with a couple more cubed root problems. They work the same on the square root, you just got to use the correct square. So here's number 5. On number 5, I'm looking for what number goes into 512 that's a perfect cube. Well, if you look over here, it happens to be that 512 is a perfect cube. The cube root of 512 is 8, so that works out pretty nicely. I'm going to do the third root of 512, which is already perfect. Now, here I do have an x7, so just like on the v7 above, I'm going to change that to an x3 and another x3, and then the one x that's left over. Again, that's 3 plus 3 plus 1. 3 plus 3 plus 1 is 7. And here I've got y squared. Now, I'd like to do the cube root of y squared, but I don't even have 3 y's, do I? So this one's non-perfect. I'm just going to have to stop right there. Scratch out your perfect ones. The cubed root of 512 is 8. Cubed root of x to the third is x, and the cubed root of x to the third is another x. These were perfect. These two are not. So when I put those together, I've got 8x squared times the third root of x, y squared. Number 7, again, it's another third root problem. I've got a 162. I'm curious over here which one of these goes into 162. I play around with my calculator a little bit, and I find out that 27 right there, 27 goes into 162. So it happens to be 27 times 6. So I've got the third root of 27 and the third root of 6. This one is perfect. This one is not. I've got a 8 this time, so I've got to get perfect thirds out of an 8. So that's going to give me a third root here, another third root here. That's 3 plus 3 is 6. I still got 2 more. And the third root of a squared. Again, 3 plus 3 plus 2 gives me this 8. Now the b, obviously there's no 3 in there, so I'm just going to have to leave it as the third root of b. And now I'll write out my perfect ones. The perfect cube is 3. Perfect cube here is a. Perfect cube here is another a. And that leaves me with a total of 3a squared times the third root of 6a squared b. Number 9, I'm looking at the 40. Again, it's a third root, so I want to know the third root here. I come over here, which one of these perfect thirds goes in, and it's going to be the 8. So I know 8 times 5 is 40, so I've got the third root of 8 times the third root of 5. And now all of these happen to be multiples of 3. Now, if you've picked up on a shortcut from here, you can probably already understand that if these are multiples, you can just divide that out. So I can do 3 goes into 6 2 times, 3 goes into 6 2 times, and 3 goes into 3 1 time. I should end up with a 2, 2, and a 1, but let's do it the long way just to see. And indeed, that is the long way, when you have to break everything down into those perfects. Eventually, you guys will end up with a lot of practice finding all the shortcuts, and you can divide these out. And there's the answer I was looking for. I've got 2m squared, n squared, and p to the 1, just like I thought, 2, 2, 1. And then I do have this third root left over. So again, those are just the odds. Take a minute to try the evens on your own. Go ahead and click pause. And here are the answers to the evens.